begin to think about modeling with linear functions, there is a set of strategies that we want to utilize in order to do that. First, we'll want to identify what is the changing quantity and then define descriptive variables to represent those quantities. When appropriate, sometimes we want to sketch a picture or define a coordinate system. We'll want to look for information that provides values for the variables or values for parts of the functional model, such as slope and an initial value. Then we want to determine what we're trying to find, identify, solve, or interpret. We'll identify a solution pathway from the provided information to what we are trying to find. Often this will involve checking and tracking units, building a table, or finding a formula for the function being used to model the problem. We'll oftentimes need to write a formula for the function, solve or evaluate the function using the formula, and reflect on whether our answer is reasonable given for the situation and whether it makes sense mathematically. Finally, we'll clearly convey our result using appropriate units and answer in full sentences when necessary. Now, not all of these steps are utilized each and every time, but we'll try to talk through each of them as we approach the problems on the following pages. So a company purchased $120,000 in new office equipment, then expect the value to depreciate or decrease by $16,000 per year. Find a linear model for the value, then find and interpret the horizontal intercept. And if you recall, the horizontal intercept is in fact the x-intercept. And determine a reasonable domain and range for the function. So what's changing is every year we are decreasing. So I'm going to let the year represent the variable time. And then therefore the value is dependent upon what the time is. So I'm going to let value be dependent upon time. So our input is going to be our time in years. And dependent upon that time, our output will be the value, which of course is dependent upon time. Well, we have some of the things that we know. We know that we originally purchased for $120,000 and we are decreasing by $16,000 per year. So I can immediately grab a linear equation that the value is equal to $120,000 minus $16,000 per year. So we found a linear model, then find and interpret the x-intercept. Well, the x-intercept is on the x-axis. And when we are on the x-axis, our y value is 0. So if we think about this, we want to know what is our horizontal intercept, which means our y value is 0. So in this case, time, and then our y value is v of t. So I'm going to substitute into the linear function we just found 0 in for v of t and solve for time. How long will it take for our value to be $0? So when I subtract 120,000 and divide by negative 16,000, t equals 7.5. This tells me that it will take 7.5 years to have a value of $0. So it says not only find, but interpret. So this particular x-intercept tells us that it will take 7.5 years for the value to be $0. Now we need to determine a domain and a range. Well, our domain is our time. Well, and if we're thinking about time in relation to value, our time should be less than or equal to 7.5, but yet greater than or equal to 0 years. And then our range, which is talking about the value, the highest value that our equipment can be is 120,000. And the lowest value it can be is $0. So in connection with this particular problem, it makes sense in the context of the problem that the domain and the range should follow where they are their highest and their lowest. Jamal is choosing between two moving companies. The first is U-Haul, charges an upfront fee of $20 and then 59 cents per mile. The second budget charges an upfront fee of $16 and then 63 cents a mile. When will U-Haul be the better choice for Jamal? All right, so if we're thinking about input, we are inputting the independent variable in this is miles. And let's represent that by M. And well, our output is going to be the value depending upon if we have U-Haul or budget. So I'm going to say U-Haul is U of M. And then we'll let budget be budget of dependent upon miles. Well, U-Haul charges a fee of $20 plus 59 cents per mile. But budget only charges $16 and then 63 cents per mile. When will they be the better choice? So let's talk about when they're going to be equivalent to one another. When are they going to be equivalent to one another? So 20 plus 0.59 miles. I'll subtract 16 from both sides such that I have 4 plus 59 cents a mile is 63 cents per mile. Therefore, 4 is 4 cents a mile when we subtract. And they are going to be the same cost if we are at 100 miles. So now I'm also bringing into the equation utilizing Desmos to help us graph. So I have our two equations and I'm substituting U of M and B of M utilizing Y so that it would graph appropriately for us. And my first graph, the red line is interpreted of the U-Haul and the blue line is budget. When I'm looking here, I do see that we have at 100 miles, it will cost us $79, and that is where they're equivalent because that is where they intersect. I also see that if I have 100 miles, my less than 100 miles, notice my red line, my U of M line is on top of my blue line, which is the budget. However, as I go over 100 miles, budget is more expensive and U-Haul is underneath because our Y value is representing how much it costs. So then we'll just make a note here. Notice that our U-Haul line is under the budget line after 100 miles. Thus, if Jamal has more than 100, not 1,000, 100 miles, we will use U-Haul. If he has under 100 miles to go, we will want to use budget. A company's revenue has been growing linearly. In 2012, their revenue was $1.45 million. By 2015, the revenue had grown to $1.81 million. If this trend continues, predict a revenue in 2020, and when will the revenue reach $3 million? Let's stick that in there. 3 million. Let's define our input as X. Or you could use T for time if you want. But we're going to let it be years since 2012. Thus, in 2012, we will be at 0 because it's since 2012. The output, our function, is the company revenue. We know a few things given the information. When time was 0, so we are at ground base of 0 being 2012, we had a revenue of 1.45 million. We also know that 3 years later in 2015, so 3 years since 2012, our revenue was 1.81 million. Now we can create, it says it's growing linearly, which means we can use y equals mx plus b. In order to use y equals mx plus b, we first need to identify the slope. But now that we have 2 points, we can easily identify that slope by finding the difference in our y values over the difference in our x values. Since we are positive, we are gaining 0.12 million per year. We also, because we defined our x value to start at 0 with 2012, we already have our y-intercept. We have a full function then. 1.45 was our starting point, and then we're gaining 0.12 million per year. Well, our A portion is asking us to predict the revenue in 2020. Well, we want to know what is the revenue in 2020. Well, 2020 is 8 years after 2012. So in this instance, X is 8. And I can easily find what is the revenue, which is our function value, by substituting in 8 for X. And this will give us approximately $2.41 million. What about in part B if we want the revenue to be 3 million? Well, we want to know what if we have 3 million, what is the time that it will take to get there? We don't know how long it will take to get there. So in this instance, since I'm given the revenue, I will say this is 3 equal to 1.45 plus 0.12x, and then solve for x. X is approximately 12.917. So nearly 13 years after 2012, that would give us then approximately just before the year 2025. So how can I use graphing technology to help me with this? So I've done a few things so that we can see how I can identify the locations of the different points. I have the blue line is our function. And then I said x equals 8. Well, x equals 8 is here, and we are trying to find where does x equal 8 intersect with our blue line. So when x was 8, so this was years, it found the intersection of $2.41 million, just as we had algebraically found above. Now, when I was looking for 3 million, so this is years, and this was dollars, I said, when is y equal to $3 million? So this is that horizontal purple line you see. And I see it intersects at 12.917 within my blue line. So this was $3 million, and this is how many years after it would take. So what I like, and then I added the labeled points just so you could clearly see where they connected with each other. Those points are something I put in there. You wouldn't necessarily need them. You could click on the gray dots and it would give you that information when you have them graphed. But it's a really great way to double check our work and make sure that things make sense in the context of the questions that are given. When a company produces Q amount of items, the total cost is the total cost of producing those items. The total cost includes both fixed cost, which includes startup costs like equipment and buildings, and various variable costs are which costs that depend on the number of items produced, like materials and labor. In most simple cases, the total cost is equal to fixed costs plus variable cost times the number of items that we have. The revenue is the amount of money a company brings in from sales. In most simple case, revenue is equal to the revenue per item times how many items that we have. The profit is the amount of money brought in after expenses. Profit is equal to revenue minus the cost. And the break-even point is when our revenue is equal to cost or when our profit is exactly zero. So in this next example below, we're going to kind of put all those pieces together in a graph form to determine what is that break-even point. So a tech startup company is looking at developing and launching a new mobile app. Initial development of the app will cost $300,000, and they estimate that marketing for each user will cost 50 cents. So the variable here is the user. So I'm going to let x equal how many the number of users that we have. So when I'm looking at just this part, we have the initial cost of $300,000 and each user costs 50 cents per user. So when I'm looking at the cost, our y value or our function is equal to $300,000, the startup, plus 50 cents times the number of users we have. However, the revenue they estimate will bring in, so they get to bring in, so this is our revenue, is $2 per user. So we're still using X as the number of users. The cost then per user to get for the revenue, Y is equal to 2X. So what does this look like then? So the blue line is the cost. The green line is our revenue. Where they intersect is the break-even point. Remember, our X value represented the users and the cost value is the Y value. So the Y value is the dollar amount. So in order to break even, the company will need to have 200,000 users to break even. Well, if we're thinking about revenue and cost, it's natural for us to want to think about supply and demand. So in economics, there is a model for how prices are determined in a free market, which states that supply and demand for a product is related to the price. The demand shows the quantity of a certain product that consumers are willing to buy at a certain price. The supply relationship shows the quantity of a product that suppliers are willing to produce at a certain sales price. If P is the price of a product, then the quantity sub D is the quantity demanded and Q sub S is the quantity supplied. The equilibrium price is the intersection of the demand and supply. Let's apply this in this last example. So at a price of $2.50 per gallon, there is a demand in a certain town for 42.5 thousand gallons of gas and a supply of 20,000 gallons. At a price of $3.50, there is a demand for 25,500 gallons and a supply of 28,000. Assuming supply and demand are linear, find the equilibrium price and the quantity. Let's first start off by just looking at supply. And then we'll focus on demand. So when I'm looking at supply at $2.50, I also have supply of 28,000 gallons at $3.50. So my supply of 20,000 gallons is at the price of $2.50. I also have a supply of 28,000 gallons at the price of $3.50. We can assume that these are linear as it's stated, and let's find the equation associated with this. So in order to do this, we need our slope. 350 minus 250 over 28 minus 20 is 1/8. We need y equals mx plus b. I noticed that neither one of the points that I have stated are the y-intercept. So I'm just going to use one of them in order to find that y-intercept. 250 is 1/8 times 20 plus b. 250 is 250 plus b. When I multiply, subtract 250, 0 is b. Perfect. So I have one equation, y equals 1/8 x plus 0. We're going to need to come back to this. Now let's look at the demand equations. So I have a demand of 42,500 gallons and a demand for 25.5, also associated with those equivalent dollar values. At a demand then of 42.5, we are still at a cost of $2.50, and at a demand of 25.5, we are still at a cost of $3.50. Again, we need our slope. And this actually simplifies to -1/17, which should make sense because as the cost is rising from $2.50 to $3.50, notice our demand is decreasing. So it makes sense in the context of the situation. Now we need to find y equals mx plus b. We do not have a y-intercept that is listed. So again, I will just choose one of the points in order to help us find that. So 250 is equal to -1/17 times 42.5 plus b. This gives me 250 equal to negative 250 when we multiply plus B. So B is equal to 5 when I add 250 to both sides. We now have our demand equation. Y is equal to negative 117x plus 5. So let's graph these and see where they are equivalent to one another. So I have my two equations here. Y equals 1/8 x. This was our supply. And we found our demand, which in this case is the purple line. So I'll just kind of label them on the graph itself. And where they intersect is the equilibrium, where the two equations are equivalent to one another. Well, recall that the x value represented the thousands of gallons, and our y value represented the cost per gallon. So the equilibrium is 27.2 thousand gallons at a price of $3.40 per gallon.